really wonderful to be here. So I'm going to talk about SIENA models. My goal for today is to really give you an introduction to the model. So let's see. All right, the slide's working. There we go. To really give you an introduction to the model, what it can do, why you might want to use a SIENA model. One reason might be because you're interested in questions of peer influence and want to control for selection into it, into relationships. But there are a number of other capabilities within a SIENA model. So I want to try to give you some insight into what that range is and some of its flexibility. I'm going to talk about the form of the model a little bit, with the real idea is to give you a sense of the intuition behind the model, in the sense that this is an actor-oriented model, or an actor-based model, or an agent-based model. Okay, so it's very different from many of the other statistical models we've covered, but if you can wrap your head around what it's doing from this actor-oriented basis, then understanding what the model does, interpreting the model becomes much simpler. So I'm going to spend a lot of time talking about that. I'll talk about the estimation a little bit because that's the actor-oriented nature. Go through an example and then a lab that really, we don't have a whole lot of time to get into everything that SIENA does, but I do want to show you some of the peculiarities of setting up and running a SIENA model. It's different in some unintuitive ways. All right, with that said, what is a stochastic actor-oriented model? Okay, so it's a longitudinal network model. We're talking about complete network data, okay, within some kind of bounded population. So that might be a school, might be an organization, might be a prison, some kind of bounded population where we've done our best to get ties between everybody within those bounds, or at least people within a certain role, like students in a school. Okay, it wasn't necessarily designed for ego networks. I have seen some applications on ego networks. It's a little bit funky, but it can be done. It's not the best way to answer questions of peer influence, but if a study is designed the right way, there might be a way to do that. So I'm not going to talk about ego networks necessarily, but if folks have questions about that, we can talk about what that would need. What we are doing is we're modeling change across discrete points in time. Okay, so a survey or some data gathered at time 1, another survey at time 2, more data at time 3. So similar to what Scott was talking about with the Turgum framework yesterday, the exact same data structure is what we're needing. Okay, the plus of the Zaum is that we can also model change in behaviors. Okay, so change in some kind of health outcome, change in some kind of health behavior. We're going to talk about smoking today as our example, but you could think about some other work that I've done has looked at change in weight, change in depression. What else are we looking at? Change in aspects of identity. Really, any individual level thing that changes, and we think it changes through peer influence, we might want to put into a model and test for. Okay, and I should mention, please ask questions at any time. Yeah. All right, Jim, you might want to close your eyes for this. This is my one attempt at network, at visualizing a network. I generally don't because I don't have a good reason. I'm just not good at it. And this is what comes out when I try to model a network. But I think this works in two ways. So this is Jefferson High, one of the ad health schools. It's in a white suburb somewhere in the Midwest, and all kids have to do is drink and smoke and have sex. So this is their network at one point in time, and you don't see a whole lot here. If you look, you can kind of see, so the nodes are shaded by smoking level with darker nodes at a higher smoking rate. Some darker nodes over here, some lighter nodes over here. So that's a kind of a hint that there is some homophily. And if we calculate an odds ratio, what are the odds of two smokers being connected versus smokers being connected to non-smokers, right? We see that we get a 1.5 odds ratio, which is decent indication that there's some assortativity on smoking. Okay. What we don't really see here, and I don't know if a sociogram can show this, maybe Jim knows a way, is the correlation between smoking and in degree. Okay, so smokers have slightly more ties coming into them, which could mean smokers are more popular in this school. Again, there's nothing much to do. So if you're smoking and you've got the booze and the cigarettes, maybe you're more popular. Okay. All right. So with the SIENA model, one thing we might want to try to do is try to understand what led to these patterns. Okay, what led to this? And as we talked about already, that could be peer influence or selection. All right, so here's the problem. All right, we're observing a network at time t, and we see that, okay, smokers are friends, and we see non-smokers are friends. All right, but what led to that? So we often think it's the peer influence, right, where people might have been different initially, but then influence one another such that over time they become more similar. Okay, but the alternative is that maybe there was, they weren't friends, or they were friends with different people, and at the next point in time, we see that they're drawn towards friendships with those who are similar in smoking. Okay, so the point is the same pattern that we observe could have been produced through multiple processes, and these are just the two that we focus on the most. We'll talk about some others later. More generally, this is a pattern of popularity, right? Where we've got the smoker receiving more ties, the smoker more popular. What preceded that? Well, again, it could be that B was already more popular, right? So B took up smoking. Or it could have been that B started smoking, and then that was what led to more and more friends. Okay, so it could have come either way. So any kind of network behavior association, we want to think, was this produced through some kind of behavior change, where the network kind of set the stage for some individuals to change their behavior, or was individuals' behavior kind of already where it was, and that led to certain network selection processes. Okay, you can tear apart most or kind of distinguish most patterns that way. All right, so we want to try to discern which routes led to these patterns. Because most people are interested in behavior as an outcome. Okay, a SIENA model can model the network as an outcome and the behavior as an outcome. Most people are interested in the behavior, so if we want to understand peer influence within natural settings, we need to think about how people selected into those relationships. Okay, and so the homophily is important. If popularity could be at work, we want to think about that. We want to control for that. Okay, so that's selection based upon the specific behavior that we are interested in. Right? That's that reverse causality. But we also want to think about selection and influence on things that are associated with the behavior. Okay, so it might be that in this school we looked at, the boys are smoking and the girls aren't. Right? So the boys are all hanging out together because that's what we do. Girls are doing their thing, and so you see this homophily on sex. That brings with it homophily on smoking, right? If it's only boys who are smoking. Okay, or it may be that smoking is associated with drinking, right? Drinking leads to smoking. Okay, in which case, if people are associating because they drink, it's not easy to get alcohol as an adolescent, so you kind of cluster on who has access to alcohol, and then you start smoking together as a kind of product of that. We're already breaking the rules, we might as well. So there might be something about alcohol use leading to smoking. Right, so if you can imagine, the pathways get pretty complex. We've got multiple kinds of things that might be happening. Selection on multiple behaviors, influence on multiple behaviors influencing one another. So we want to try to wrap our head around all of those. It's also possible that network processes can amplify the level of homophily, right? So in the example here, let's say A really wants to have friends who are like them. Okay? And so A only befriends people who are like them. So A is a non-smoker. Right? A can't stand smoking. I'm only going to be friends with people who don't smoke. Right? Over time, A's friendship with D becomes reciprocated. Right? Because that's what we do. So this now D thinks of A as a friend. I'm sorry for those in the back who can't see. But D becomes A as a friend. That tie is driven by reciprocity. D may not care about smoking, not smoking, right? Kind of indifferent. But we now have a tie that is between non-smokers, but is not driven by similarity in smoking. Similarly over here, if B and D form a tie, it's a tie between two non-smokers. It looks like homophily, but it might be driven through transitivity, just because we've got a friend in common. Okay, so again, we want to think about these other processes that are at work and driving friendship and can create the patterns that we're interested in, but aren't the source of those patterns. Right? So simply seeing homophily doesn't mean it's a preference for homophily. That's what I've tried to emphasize in my work over the years. Okay. All right, so when do we want to use a Zaum? Okay. Questions about how networks affect individual behavior, right? Peer influence, diffusion, things like that. We also might want to think about it if we're simply interested in network change. Okay, we're not interested in any kind of behavior. We just want to model how a network evolves over time. Maybe it's testing out different processes that could lead to homophily. I've done some work looking at whether kids who are at risk for depression are more likely to kind of withdraw from social interaction, or if they're excluded from others, kind of excluded by peers as a result of that depression. More generally, questions about how do we acquire the networks? How do we acquire those peers who influence us? I think that if we really believe that peer influence is operating, we need to look at the other side and figure out why is it people have the network positions and the network structures that they have. So we could use a Zaum for that. So Scott talked about tergums yesterday. Most questions that you would want to address with a tergum, you could address with a SIENA model. There's some differences in assumptions, but in general, if you're thinking about network change and you've got discrete panel data, you can use a SIENA model. Okay? You might also be interested in questions about how do networks and behavior change, and how does that accumulate into macro levels, prevalence levels, or thinking about questions like cumulative disadvantage, right? So if we have behaviors clustered within groups, and we might see those groups kind of diverging over time or polarizing over time. And so we can use a SIENA model to model these processes, and then some of the simulation capacities or other kind of decomposition methods to try to understand which of these micro-level patterns is responsible or shares more responsibility for any macro-level patterns that we observe. Okay. One of the kind of almost overwhelming things about a SIENA model is that you can have multiple outcomes. There's always at least one network outcome, but you can have a second network, a third network. You can model multiple networks evolving over time and influencing one another. So we're going to be talking about friendship, but if you had a network of kind of status between peers, a network of who studies together, a network of who shares needles together, right? I don't think that was necessarily happening at Jefferson, but you could put all of these, and it would be a mess of a model, but you could look at these multiple kinds of networks. You can bring in multiple behaviors: smoking, drinking, mental health. You can bring in two-mode networks. So we could think of people at different kinds of contexts, different kinds of foci. So we could think of students in different activities, students in different classes, students in maybe different informal spaces where they hang out. We can model all of those over time and their interrelations. Okay. All right. So and thinking about kind of the different models and things you've talked about this week, we can think about the kind of network models on two levels, right? Are we using the network to explain some individual behavior, in which case we've got a series of models that we might want to use, varying complexity depending on how much of the network structure we want to try to account for. Okay, the general linear model, we may not be accounting for anything, right? But we get up here to some of these other models, we're accounting for interdependence between people in a network. We also have models where the network is the outcome. Okay, we've talked about some of these, a QAT model, ERGM model, TERGM model, where the network is the outcome, and individuals are more or less stable across time. All right, so the SIENA model, the Zaum brings those in and models both at the same time, okay, and allows them to shape one another. There's a merging model. There's a paper on it just this year that is a cross-sectional model that gets at selection and influence. I'm not sure how that works. I haven't wrapped my head around it yet, but it's basically it's built on the ERGM framework. So if you're really interested in these questions, stay tuned to see how people use. Yeah. So the relationships are the outcome within. Yeah, you got it. All right. Yeah.
I know you mentioned early on that this is not ego networks, but I was just wondering, maybe it's not peer influence, but something like in like a health discussion network changing behavior, something like that. Is it possible to model in an ego network kind of similarly to track influence?
It could be, yeah. The challenge with ego networks is you don't have the opportunity pool of possible relationships. So the trick to make that work is it's what Bria talked about. You have those alter-alter ties, which maybe they're there, maybe they're not, and you can treat alter-alter ties as the ties of interest. The other challenge is to model any kind of change, you need good behavior on those alters and their change over time. And if that's coming through ego, how well can ego report that, right? Given things like self-attribution bias, and so it's challenging. But I've seen it done in terms of modeling change in structure, and I think that can there's something there. It would be harder to meet those just face validity, I guess. But maybe you can do it. That's your challenge. Okay, so so because the SIENA model and the TERGM do quite similar things on the network side, I just want to touch briefly on what we're doing that's different. Okay, so the TERGM and the STERGM, and we talked about yesterday. So here we're taking a model at one point in time and then modeling discrete change to the next point in time. Okay, and we're modeling the ties themselves. Okay, which ties have changed, which ties are the same. It's very much a regression of one time point on the previous time point. The Zaum is a very different mindset. Okay, the Zaum is it's this actor-oriented model where we're taking the observed network at time one. Okay, say we're going to start here, and then we're going to put this agent-based model on top of it, where we kind of pick actors and allow them one by one to change one tie. Okay, and we're going to put some effects in a model to determine how actors choose which tie to change. Okay, but we're going to go through this kind of one tie by one by one. And eventually, right, if our model fits well, then over a long series of these changes, we get a network at time two that looks a lot like the network that we observed at time two in some important ways. Okay, this is a way of implementing an MC-MC algorithm. It's taking it down and implementing it from the actor's perspective. Okay, so let me show you how this works. See if we can. Actually, I think I've got this queued up here. All right, so here is a visualization of just network change. We're not interested in behavior change yet. You can't see that. Oh, my apologies. Okay, so here we have a visualization. This was done with Jimmy Adams of what is the SIENA model doing kind of when you're just staring at a screen, what's happening in the background. If you can see here, there's one node that's red. This node has been randomly selected to consider changing their network. Okay, and so keep an eye on it, and let's see what happens. They add a tie. All right, and the network shifts. The algorithm then moves and randomly selects another actor right here. Okay, we're gonna let that actor consider all possible ties. I forget what effects are in the model here, but they're considering all ties, and they're going to make that change that maximizes their utility. And we'll talk about what that means. Okay, what do they do? They don't do anything. Okay, they're happy where they are. All right, but now we've got another node up there at the top that's primed to consider changes. Looks like they dropped a tie. This is like, where's Waldo? Right, there's a red node here somewhere. There it is, down here. Okay, so what are they going to do? Oh, they dropped a tie. Okay, now we're down here at the very bottom. What's that person? That person did nothing. Okay, you can run through it, right? Kind of track how the network changes over time. Again, this is part of building that intuition. How is the SIENA model assuming change occurs? Okay, and it's this really step by step thing. Happens much faster, thankfully. Not fast enough still, but all right. All right, so that's the idea. Yeah, go ahead. Okay. Yeah, so I'll talk about that in a moment with ways to think about whether some actors are changing more rapidly and how to designate that. When we get to rate functions, that's going to be the way to do it. All right, how are we doing here? All right, I think I'm actually going to skip this. Little ditty in R, and talk more about the model itself. Okay, so it's a stochastic actor-oriented model. Before that, it was a stochastic actor-based model. Before that, it was a SIENA model. So you're going to hear all these different names. SIENA actually stands for Simulation Investigation for Empirical Network Analysis, which is a way that, I don't know, Tom Snyder's, I think, really was fascinated by Siena, the town of Siena in Italy, and wanted to name his model after that. I think he did present it there first in terms of presenting it to an academic audience. But it's affectionately known as a SIENA model. But when we write about it, we use this more technical language. It's in our SIENA. We'll see that shortly. And again, it does this nice thing of estimating, right, network and behavior change and more than that. All right, so how does this work? Okay, well, we've got two discrete waves of data, at least, that we're looking at. We're assuming continuous time between those two waves. So we're assuming there's all these microsteps, thousands of microsteps between these, and we're going to model what happens across these microsteps. Or we're going to imagine what could happen, right? We're actually going to engage in kind of a hypothetical exercise wherein between these waves we say, well, what if actors follow these rules? And then we see if actors following those hypothetical rules produce a network like we observe at time 2. Okay, so it's really an agent-based model at the heart of it. One of the assumptions is that actors control their outgoing ties. Okay, so I control who I say is my friend, or who I say I get advice from, or Actors also control their behavior. So this kind of data or model really wouldn't be appropriate for, well, there's a variation that does allow for some bilateral kinds of things. But it's tricky if you have networks where people or actors don't control their ties. Okay? So the model itself is specified as two functions, two for network change, two for behavior change. Okay, so when we're talking about modeling change in the network, we've got a function that determines when do changes occur, how often do actors have an opportunity to change their ties, and then when an actor has a chance, what tie do they choose? Okay, we tend to focus mostly on this question, right? Who do people choose? And tend to assume that this is uniform, right? Everybody's got equal opportunities to change. But if there's something that people move into a new context or something, the question that came up earlier, you can adjust this. Rate function gives some actors more chances to change. Actors with some attributes might have more chances to change. You might imagine in a school, freshmen entering the school are changing their networks a lot more rapidly than older students. So that's something that could be put in there to test for that. Similarly, on the behavior change side, we've got a function that's how often do actors change their behavior. Okay, and then when an actor is chosen to change their behavior, what behavior do they choose? What level of a behavior do they choose? Okay, so the objective function looks like this. I'm not going to get too much into this. What I do want to point out, though, is it does have this linear form where we've got a series of effects, beta, a series of or coefficients beta, a series of network effects. These SKI are different network configurations, things like reciprocity or transitivity or homophily that are applied to the network at its current state and inform these actors' decisions. Okay, so during model fitting, we're doing kind of the same thing we always do. We're trying to come up with a set of coefficients. All right, so what does that look like? Because this is where it starts to really get somewhat different from other modeling. So again, we're taking an actor-oriented perspective here. Okay, so during estimation, actors are randomly chosen to change their ties. Let's say we've got a model that's set up like this. It's got an out degree parameter. This is like an edges term in the ergo model. Okay, and it's an effect that gets at how many ties do I have, right? If I add a tie, how many ties will I have? We're going to say it's got a -2 as a coefficient. Just assume that's the case. Reciprocity is this: if I send you a tie, are you sending me a tie? Right? That's got a positive coefficient. So let's say this is our hypothetical kind of model, right? We're going to test this, whether these parameters work. And so let's say in our network here, ego is chosen to change their ties. Ego is going to go through every possible tie in the network, go through every alter, and consider what is the value of changing that tie. Okay, ego has a tie to J1. What would happen if ego changed that tie? So if ego dropped that tie to J1, that would reduce ego's numbers of ties to 1, okay, which gives us a -2 from this part of the equation. That would be dropping a reciprocated tie, so ego would have no reciprocated ties, so that would give us a 0 here. Works out to be a utility of -2. Okay, ego could also, not change any ties, drop a tie to J2, add these other ties. For each of these, we're going to say, what would that, how would that affect these two statistics in the model? And you can follow the math there. I'll let you do that on your own. But it works out to be each tie, potential tie or dropping a tie, has a different utility according to the current model, okay, according to the current set of coefficients up here. Okay, and so based on where we are now, dropping the tie to J2, which is adding a tie. Adding ties are costly, having ties are costly, so dropping that tie is good, if, especially because it's not providing any benefit. It's not a reciprocated tie, which actors value. Okay, so ego's likely to drop that tie. I should mention, we add a little bit of error. The model adds a little bit of error to make this stochastic. Right, so in case there's a tie, there is some error added in there. All right, so ego drops that tie, and then the model would select another actor who would evaluate the current network, right, with the tie from ego to J2 dropped, and evaluate all possible ties and make make their own decision. Okay, so you can imagine over time, ego might drop the tie to J2 now, ego might add it later. Right, we could see ties coming and going between. Right, this is a simulated sequence of changes between our two observations. Right, so there might be all kinds of changes occurring and recurring over time. Okay, so what kind of effects do we include in the model? These are just some of the most common ones. Out degree to control for, again, ties are costly. We want to you can think of out degree as an intercept in a model to kind of keep the probability of a tie constant, or at least not necessarily constant, but to not have networks that explode with ties or have too few ties. We want to keep that probability aligned with what we observed. Network processes like reciprocity and transitivity. We can also think about attribute-based effects. So we talked about homophily, but also sociality. Actors with certain attributes might send more ties. Actors with certain attributes, right, might receive more ties. Okay, these things can be stable or time-changing. That's okay. Oftentimes, dyadic attributes are really important to control for, right? Things that bring people together, right? With students, it's being in the same classes or being in the same clubs, right? Those are really important for understanding how networks form. Okay. All right. So that's the network side of the model, and let's see. I realize. So what we're trying to do with a model, again, it might sound like we're just making stuff up, right? We're just simulating changes over time. What we're trying to do in fitting a model is we've got it 2 discrete time points, starting at time 1, and we're simulating. Okay, we've got this time 2 network that has certain properties, right? It's got a certain number of ties, a certain level of reciprocity, a certain number of triangles, a certain amount of homophily, right? It's got all these patterns in it. The model is trying to fit those patterns. So if we've got a model like we just talked about, a model with out degree and reciprocity in it, we're trying to we would take the network observed at time 2. What's the rate of reciprocity? How many ties there are? Let's try to find a model that will recreate that. Right? Find a set of coefficients for out degree and reciprocity that when we apply this simulation with those estimates, we get a network that looks like the observed time 2 network. Okay, so we're not fitting the actual ties, which ties actually exist at time 2. That would be really, really hard. Instead, we're trying to have a model that will recreate networks that have the same properties as that time 2 network. And when it comes to behavior, we've got a behavior function in there. We're testing for peer influence. We're trying to do the same thing. We're trying to come up with model estimates that when actors follow those rules, we get a behavior distribution that looks like that observed time 2 distribution. So the level of smoking is the same. The distribution of across individuals, right? That looks the same. Okay. All right. Okay. So how do we do that? with the behavior. The behavior function is in some ways simpler. It's like a multinomial logistic model. One of the kind of unique things about SIENA models is they're designed where kind of network behaviors themselves are these discrete values. Okay, so take whatever behavior variable you're used to working with and turn it into something that's ordinal, right? You've got, so smoking you saw earlier was 0, 1, and 2. If you've got something like BMI, right, this nice continuous measure, you've got to turn it into these ordinal categories. Okay, there is a SIENA model, or a version of the model that was recently developed for continuous outcomes, but there's not as much work done on that yet. So most of the modeling you'll see looks at these kind of ordinal dependent variables. So you lose some information there, and you're really just trying to capture major changes that occur, right? Going from not smoking to smoking, right? That's a big qualitative change. Okay, so we have a behavior function. It's similar in some ways. It takes a set of coefficients, takes a set of effects. Here, notice that these also include the network X, right? So the network can inform smoking, and the estimation algorithm, this simulation algorithm, looks a lot the same in the sense that we're going to randomly kind of identify an actor, give them the chance to change their behavior. Randomly identified actor can increase their behavior by one step. They can decrease their behavior by one step, or they can stay the same. Okay, so that for any actor, it's those are the three choices of what they can do, and they'll do a similar thing where they're going to consider each possible change, what is its utility based upon the current model, and then make that change that maximizes the utility. And so a behavior function, I think it's helpful really to think about this. It's different from a regression, but the regression framework doesn't break down a whole lot in terms of thinking about effects, right? So if you were going to predict smoking, well, here we have a linear and quadratic term, which is kind of like an intercept in our model. It kind of just maintains the overall distribution of smoking. Smoking tends to have this U-shaped distribution where you've got non-smokers and you've got smokers and not a whole lot of people in the middle. Okay, so you have a function, a couple of effects to control for that distribution. We've got an effect for peer influence, right? So what is the people who are currently my friends, what's their smoking level? We can look across peers and get the average of those peers, and how does that influence my level? We could also look across peers and say, well, do I have any peers who smoke? Like, what's the maximum number? Or do I have any non-smoking peers or friends? We can think of different ways of that. And then we can include a number of controls, again, similar like we would do in a typical linear model, the kinds of things we want to control for. That can include other aspects of an individual's position, though. So we could include something like in degree, right? How many people named me as a friend, right? We can put that in there, or other kinds of network, maybe closed triads. Maybe we think being within dense friendship groups has an effect on our outcome. We could put that in there. Okay, so we can have a number of different kinds of network effects. All right. So a model might look something like this. This is where we've got a linear effect, a quadratic effect to control for the distribution. We're controlling for age here, and then we've got one version of a similarity effect. Okay, this version is how similar am I to my peers, weighted by the total number of friends that I have. And so with this model specification, we could go through the same exercise where we identify a hypothetical, or identify one of the actors in the network and give them this choice. What do you want to do? Okay, well, if we choose somebody who's at level 1, they're at level 1, they could stay at level 1. they could drop to no smoking at all, or they could go up to be a more frequent smoker. And when this actor evaluates that, we're evaluating the potential new behavior, right? So we're evaluating a 0, a 1, or a 2. So we plug that into our linear equation, our quadratic equation, plug it in for multiply it by our age effect, and then we've got to figure out what that means for total similarity. I'm not going to walk through all of this, but this is the equation we're using, and it works out to be a little bit differently for each actor depending on their level. Well, the similarity in each of these has a different level, right? So ego's got a tie to J1. They're both smokers. It ends up to be this function gives us 0.95 when it's evaluated. Same as this function here. These two with different levels of smoking where there's no tie end up not changing at all because there's no tie from ego to those. So those peers are not friends. Ego's not named them as a friend, so they don't work. Their behavior doesn't affect ego at all. Okay, so this is how similarity changes if ego stays at level 1 of smoking. If ego were to consider dropping their smoking level to 0, then we calculate, well, what does that mean for the similarity in each of these dyads? Well, these drop down, right? Ego's friends. Ego becomes less similar than them, so that drops down. These other two still aren't friends, right? So they contribute nothing. So the overall similarity drops down to 0.9. Likewise, if ego increases their behavior to 2, we see that again, ego becomes dissimilar to J1 and J2, and so that similarity statistic is lower. So ultimately, we see that the similarity is greatest for staying at level 1, and the similarity would decrease for any of these two. So when we add all of this up together, the highest utility looks to be becoming a heavier smoker, right? And that's driven by what is it? This quadratic shape effect plus the age effect. The age effect really is driving this. We'd see that actually even though peer influence is a positive value in this network, ego's making a decision that makes them a little bit more different from their friends because of the other effects. Okay. All right. Any questions right now, or have I totally confused you? Mm-hmm.
I have a question in terms of the assumptions behind the utility calculation. How much do you think that there is a built-in assumption of the knowledge that each agent has of the
Yeah, I mean, so that is one of the assumptions, right? Actors are considering every possible, peer in a network to be a friend, or every possible value of a behavior. The behavior, that's probably less problematic. It's really, do you know that behavior is an option, and that's and can evaluate that. Assuming that kids in a large school know everybody else and know their attributes, know their behaviors. We're likely kind of pushing that assumption pretty far. So something like things that are visible attributes, maybe it's okay. But things that you don't see, if kids aren't smoking at school, aren't drinking at school, where does that information come from? So that one, I think it would be. I don't know what the implications are of violating that assumption, but we're always pushing that one when we're looking at the bigger schools. Now, a lot of folks are looking at smaller schools, or small schools, small settings, classrooms, right? These things where you do have the landscape, right? You can see the landscape, and you kind of know who your friends' friends are, and it's a little bit, the assumptions are a little bit more easier to meet there.
Is there
Yeah.
any study incorporating into SIENA models an amount of error for the depending on what you study?
No, one thing that has been done, Tom's been working on a model that tries to differentiate ties within a closer social distance and give those greater, allow those to have greater weight than ties at a further social distance to try to get at this kind of asymmetry in information that goes along with social distance, because to kind of test the idea that, well, most of the ties that we add are within that closer social distance with friends of friends, or at least part of the same social circles more generally. And that might be one way to try to get, he's been working on it for a long time though. So there's something really hard about that problem, but that's offers some promise. Yeah.
So all of these models then assume a fixed landscape? So like if the landscape itself is dynamic, can you also then model the network changes between these actors? Or can you have both moving at the same time?
So when you say landscape, do you mean the set of actors there, or something?
So like the physical, it's like these examples have been like abound in school. So like the school, the composition within the school is changing, but the school structure itself is not changing. So what happens like when groups of people are moving to different places?
Yeah, okay, great. Yeah, so that's fascinating when that happens. So you can imagine middle schools merging to a high school, or classroom, class assignments change from year to year. So we can handle, if we have that information, so that would be a kind of an exogenous, it would be some kind of exogenously changing covariate. Those examples would be, so we could imagine having a parameter in the model that's, are we in the same school? And that changes over time. When we're in middle school, we're in the same school, but people in the other middle school are not. But then we're all in the same school at some point. We could also imagine modeling that as endogenously. So I've done some work looking at extracurricular activities, and those change from year to year, kind of which activities kids are in. And so we could have a two-mode network that is which activities kids choose, and then being in the same activity is a predictor of friendship. And that, but that's endogenous in the sense that being friends can also lead to choosing the same activities. So you can do it that way. The only, there's not a catch, but things need to be measured at the same time points. So if change in the network is occurring different rates than change in the landscape, you'd want to try to find out a way to align those. So it's challenging with activities. They change kind of semester to semester, or in these weird, sports have these weird seasons that don't necessarily change when we're measuring our network. And so it can be tough to align those. But that's something that definitely could be accounted for if you have the data. Yeah.
With something like COVID, some big, large-scale event that's not it's outside of the network but affects everyone in the network, is that a network effect? Like, how do you account for something like that, which might have a significant impact on everyone in the network? Where do you put that into this model, or how does that fit into the objective function of the network?
Yeah. So what I would do is, ideally, we have enough waves of data that some are prior to COVID and some are after. And we could put a covariate in there for time, and test whether something is different during that that period of maybe we're all remote, and is maybe the effect of being in the same classes goes away, or gets really, really weak for that point in time, or so yeah, we can have time. So the model by default will assume that effects are constant over time, that reciprocity or having the same smoking status is constant throughout, but we can and should be checking for whether or not there's heterogeneity, and at some points in time, some of these processes are more rapid. So in some other work I've done, we see that when people enter a new setting, one of the strongest effects is homophily. Right? They gravitate towards people who are similar on visible characteristics. Right? It's about just kind of finding your place, your people. And then over time, other processes become more important. So you begin to meet friends of friends. You become similar on other kinds of hidden attributes, things like values and beliefs that are more important than just surface attributes. And so you can imagine doing, again, changes that either changes at the individual level, changes in the contextual level. You can capture all that, again, if you have the data. The data is so hard to get because you want lots of waves. Ideally, you want lots of waves to measure some of these. You need at least 2. 3 is a lot better because that's twice as many instances of change as with only 2 waves. So 3 is great. More is better, but you don't get the same boost with more waves. Yeah. So this came up yesterday, right? What size networks do we need? We need networks, probably the smallest I would say is something around 30. If you have enough waves of data that you can model change. If you only have a couple of waves of data, you want really, really bigger, larger networks to try to have the same amount of again, dyadic level instances of change. Okay. Yeah.
Is there an upper limit of what might be feasible if your model takes that?
So I've seen analyses up to about 2,000, and you could do more. You're pushing on this assumption of full knowledge of the network. So another thing you can do is look at multiple networks. You can use a multi-level strategy. So again, think of multiple classrooms within a school. Right? You could model each classroom evolving, the network and it evolving separately, and then combine those, and that can get much larger than that 2,000. That size is really for one bounded network being estimated on its own. All right. I want to be cognizant of time because we are going to jump into R. Okay, so I'm going to skip a lot of this. Okay. All right, so let me talk about how do we interpret this, because this is something where SIENA is a little bit different. So we get some results from a model. On the network side, it's useful to think about this as a logistic regression, right? Just like Scott was talking about yesterday. Think of it as a logistic regression, where the unit analysis is the dyad, and but instead of it being kind of the probability or the odds of a tie, it's the probability or log odds of an actor making a tie, selecting an alter within one of those change opportunities. Okay, within one of those small change opportunities. Okay, so the outcome is a tie. It could be forming a new tie, but it could also be keeping a tie that already exists. Okay, the model, the default model kind of lumps those together. Okay, so when you see a positive coefficient for, let's say it's same smoking status, that means that people are likely to add smokers as friends or keep smokers as friends, okay, or someone who's similar on smoking status to themselves. Okay, so it's that maintenance or forming a new one. There's also a temptation, like a logistic regression, to turn these into, from log odds into odds and interpret them as an odds ratio. And that can be helpful. The caveat there is that that's assuming that that interpretation assumes everything else is equal, right? It's held fixed at some level, and you're just changing, how does going from being same on smoking to being different on smoking change the odds of a tie, holding everything else constant, all right? Well, that might be a really big kind of assumption to make. It's problematic sometimes because with networks, we oftentimes have effects that are interdependent, right? So if we have a model that has homophily on smoking, but it also has a popularity on smoking effect in there, that means that both of those effects change or are impacted or come into play if I change my smoking status or a partner changes their smoking status in this kind of hypothetical scenario. And so you want to kind of sometimes have to look across multiple effects to understand the implication of such differences. Okay. All right, when it comes to the behavior function, so this is we can interpret effects as how does a one level change, one unit change in our predictor affect the log odds of being at a certain level of behavior versus one level higher, right? So we're talking about one level difference here. That could be, so the effect doesn't necessarily mean someone's increasing their behavior. So specifically with a positive coefficient doesn't necessarily mean that having this thing makes people's behavior increase. Okay, so a positive peer influence coefficient, right? Look at that and say, oh, wow, peer influence is positive. So people are increasing their behavior in response to their friends. Well, that's one possibility. But it could also be the case that, right, if my peers aren't smoking, peer influence might lead me to not smoke, right? So it might lead to a decrease in my behavior. Okay, so so I want to kind of push you to think that these coefficients do not necessarily, remember, these coefficients do not necessarily, you're not predicting the level of the behavior or the direction of change in the behavior. It's different from models of change in that regard. Right? Instead, you're predicting how this, or calculating how this affects the level of the behavior that's most attractive. And so, all right. All right, so I've got a number of examples in here. I don't think I want to go through all of these. I hope it's detailed enough that you could go through it on your own and try to understand what each of these effects are getting at. But this is a typical SIENA model, right? This is a behavior or a network function. What's that? About 25 effects, and that's probably an average size. Right? We're interested in this example, smoking. So we've got some effects for smoking in here, but we're controlling for a bunch of other things that people select ties on. Some network stuff, being in the same activities, gender, age, delinquency, alcohol use, and grade point average. Okay, so we can go through a lot of these. One I do want to show you is this smoking, right? This smoking status. We've got a positive effect for homophily, a positive effect for smoking alter, implying that homophily is present, but alters are also popularity. To really understand how smoking affects friendship, we've got to interpret these in combination. Okay, and so that's what we're doing down here, is we're calculating for different combinations of ego and alter smoking, what are the odds of a tie, and how does that part of the objective function I showed you earlier, where we worked through all of that? Well, we could just pull out the two smoking effects and look at what does it mean? How does an actor who's a non-smoker, and these potential alters, kind of ignoring the rest of the things. What does that contribute to that function? And we see homophily, non-smokers choosing non-smokers, a little bit stronger homophily with smokers choosing smokers, a little bit stronger tendency for those relationships to form or persist. And then a really strong aversion here where smokers are not befriending non-smokers, non-smokers also not befriending smokers, but not necessarily as strong. I'd actually expect that to be the other way around. But again, this is Jefferson High, and things are different there. This is the contribution to the behavior function. So it's and that's a log odds. Yeah. You can actually come back and turn this into odds and might make it a little bit more interpretable. But the basic idea is you compare these different scenarios and try to get at the sense of which scenarios are more or less likely. Okay, here's what a behavior function would look like. We've got our distribution effects earlier. These are all just effects of different attributes. And then our average similarity stands out as being the strongest, almost the only effect here. So you can walk through and look at what these mean. This is the U shape for smoking that I mentioned earlier and how that's calculated. Here is how we think about average similarity. Average similarity, it turns out to be something that ranges from 0 to 1, where 0 is the most dissimilar, 1 is absolutely similar. So we're looking at how, when we're talking about how average similarity, an effect here, we're going from all my friends, a 1 unit change means we're going from all my friends are maximally dissimilar to all my friends are as similar as possible, and how does that affect my behavior? And you see that has a pretty compelling effect, right? You would exponentiate that to get the effect, but you're really likely to follow your friends here. Okay. All right. I do want to mention that we do goodness of fit the same way that we do for ergoms, right? We do these, calculate how the model is able to reproduce statistics from the observed network. With behavior, right, we could look at the distribution and how we're able to recreate that distribution, but also some other, we could think of other more developed kinds of measures. All right. Yeah. All right. The last thing before the lab, I want to just mention, there are some resources out there, and I really, would encourage checking out good overview article. It's still good, even 14 years later. This really captures the model. But Tom Snyder's has a website with an immense amount of information. A manual, probably 200 pages now, that really is essential if you're going to be modeling, because it helps to explain the kinds of effects, how the model works, the kinds of data you need. It really is, it's one of the most detailed models or manuals I've seen. But also, he mentions workshops, because if you're going to be doing this, I know a few people who've picked this up on their own, and I'm very impressed that some students can. But there's some kind of week-long workshops here in Europe that are incredibly useful. Okay, I need to jump into this lab, or we're never going to get there. So while I'm shifting over, does anybody have questions? Yeah. Definitely. Yeah. So I wish I had 3 hours because that's at the back end of the slides a little bit. So we can't. So and I should mention, so for the network, we can separate out adding a tie and have a set of effects for that and parameters for that, and maintaining versus dropping a tie. And those can be separate models. So a lot like the Sturgeon, you can have separate models for those two. You can do the same thing on the behavior side. You can have one set for increases, one set of effects for decreases. And in fact, we did that with smoking to try to get at that, and your intuition's right on. We found that there's strong influence right here, like you see, when you kind of specify a separate effect, kind of almost think of it as an offset, but if we're considering, if I'm considering decreasing my smoking, what is the effect of peers for that kind of decision? It's peers, like they don't matter at all, right? Their influence goes away. It's all in that upward direction. So what it's really doing is it's taking that behavior function. You can really think of it as it's two behavior functions that are constrained to be equal, one for increases and one for decreases. And the default is keep those equal, but we can free up, equivalent of freeing up parameters. So yeah, happy to talk more if you want. Yeah, so that's one area where the SIENA model is different from the Sturgeon. The Sturgeon requires that you specify what is my model for formation, what is my model for dissolution. The SIENA model keeps everything constrained to be equal for those two, and you have to come in and decide if you want to free them up. So, all right, so, okay, hopefully you've got the script open. I'm just going to get it going here. So we're working with a smaller set of data that comes with the SIENA package. These are 50 Scottish girls who are learning about smoking and drinking. And so they're learning from each other. Not to spoil the punchline here, but okay. So what I want to do is show you kind of how the data are structured and kind of some of the steps to get that kind of manipulated into something that SIENA will use. So alcohol use, let's see, is in this thing called S50A. It's a data frame. I realize I'm working in R. You're probably in RStudio. You can actually probably see the data better than I can. But if we look at the first 10 rows, right, we see 3 columns: alcohol use at time 1, time 2, time 3. It's this nice ordinal thing here. Looks like it goes from 1 to 5. The documentation tells you what those are, but 5 is the highest level of use. 1 is no use. And if we look at, this is just the frequency distribution across waves, right? We see that there tends to be, you can kind of see some increase in alcohol use across time. Okay. We could look to see how much change in there is there. So we see that about 50% of girls change from time 1 to time 2. Okay, so there's some change here. Not so much change, right? We need some stability there as well. Okay, all right. So we've got alcohol use. That data structure is probably like what you're used to, and we've also got networks here. So those are S5051, which is the time 1 network. It's a matrix. If you see here, it's a 50 by 50 social matrix. I'm going to put these into a list because that'll make some things easier later on. All right, and if we look at this, so one thing is we need to have the same set of actors at every time point. Okay? Even if some kids come and go, we can account for that in some different ways, but it has to be the same dimensions across each time point. Okay, so we've got 50 by 50 in each one, and Yeah, and for our network, it's a square matrix. If we're doing a two-mode network, right, people choosing activities or something else, that's okay. It wouldn't be square, but we would do some things differently. Okay, we've got 113 ties, a few more across our 3 time points, and no missing values. That's important to know. SIENA won't blow up with missing values. It does have some imputation along the way, so you can still estimate your models with some missing values, which do cause trouble in certain ways with ergoms. Okay, so we want to make sure that we have enough stability, right? Balance of stability and change. So the Jacquard coefficient is a good measure. It's the proportion of ties that are stable out of the proportion of ties that are the same between 2 observations out of all ties that are present across the 2 observations. Okay, and so we see here that is 0.33. So a third of ties that are ever observed are observed at both time 1 and time 2. If we look at time 2 to time 3, we see 38% of ties are observed, and that's good. So for our SIENA model, we want at least 0.2. If they're small networks, a little bit larger is better, just so we have enough kind of information to kind of anchor things. Okay, so I'm going to stack these into an array. So stack these 3 networks into a 3-dimensional kind of array. And that's going to make it easier to load them into SIENA. All right, so we see we've got a 50 by 50 by 3 thing now. Okay, we're going to use some colors later. All right, let's take a look at these. Okay, what happened? Let's try again. Dun, dun. All right, there we go. Oh, I missed a step.